Come on, everybody! Walking Mr. Sunshine. Na 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 na, Katamari on the swing. Na 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 na, Katamari on the swing. 今始まるよ君と僕の未体験アドベンチャー。スカイ照らしてよ、お日様は僕らのスポットライトさ。おスマイル聞こえるよ、都会のシャレたスイングビート踊ろうよ。Dance, dance, dance くるくる回る雲を突き抜けて、君と転がりたい愛のかけらを集め空に浮かべよう。 Yeah, how can miss the sunshine? ななななななななな、僕らのシンフォニー。なななななななな、はじけるファンタジー。今始まるよ君と僕の未体験アドベンチャー。照らしてよ、星空は僕らのブラックライトさ。タキシードシャレして踊ろう、僕らのリズムで流行りのステップステップステップ。風切って回る視線は国付けさ。君と固まりたい二人は運命の中に巻き込まれたんだ。Oh yeah, how can miss the sunshine? なななななななな、ときめく destiny。 なななななななな、やっぱり I love you。 今日もどこかで出会いまれる愛に焼けた肌。
Hi, everybody. Welcome back to Chem 140. We're done with exams, and that is all behind us for quite a while, and then we'll have to do 2 of them all at once, because that's how midterm number 2 and the final work. They're practically on top of each other. There's a question in the chat. Where's the extra credit for the exam posted? So I offer more questions than there are points, so there are no specific questions that are extra credit. There are 75 points possible on your exam, but there are 83 points available. So if you do 75 points worth of questions correctly and then get 8 points worth of questions wrong, you still get a perfect score. If you get every question right, I give you more than 100%. So I give you more points. That's where the extra credit comes in. It's not really extra credit. It's just, I am rewarding students who know more than 90% of the content. Another way of me saying it is that I don't think that you should need to know absolutely everything to get 100 in this class. If you make a few errors, that's fine. Like, it's good enough, right? So that's how I assess you on the exams. What do we have on the agenda? Just the quiz number 4. So that's due on Tuesday. Make sure you get that in by the deadline. There is a 24-hour period after that if you need it to turn it in. On Tuesday, tomorrow, we're going to go over lab number 3 in more detail. I am still currently grading your lab number 2s. The issue I'm running into, though, is I just haven't had time. I'm like 40% of the way through labs right now, so I'm gonna keep working on it throughout the week. So bear with me. All right, Unit 9 is where the class starts to get into more involved topics. Today we are going to talk about ionic bonding. On Unit 10, we're going to talk about covalent bonding. And then in Unit 11, we're going to start naming stuff. So the class does get a little bit more difficult. Not necessarily starting with today, but in a few days, what I like to call the pleasure cruise part of Chem 140 comes to an abrupt end. And it's going to be time to really buckle down because the topics will get much more difficult much more quickly. For sig figs, do you do the sig figs at the end of multiple calculations or at the end of each equation? Do it whenever you change operations. If everything is multiplication, you could do it at the end. But if you had to do addition, then multiplication, then addition, then division, then subtraction, or whatever, every time you change rules, you have to resolve all your sig figs because you can't just carry 3 to the end. It doesn't work like that. All right. Where'd my pen go? There it is. So the first thing that we're going to discuss is we're going to go back to Unit 8 for a bit, and we're going to talk about what groups and periods represented in terms of the physical nature of an atom and how its electrons are arranged around it. That's going to be very important. Sorry, I'm scratching my head and bending my neck, and I think I moved the mic on accident there. Now, why is that going to be important? The reason is that the electronic structure is going to affect how bonding occurs, and bonding is going to be a very important topic to discuss how chemistry happens. When we do chemical reactions, we create and remove bonds. A chemical bond is going to be defined as any attraction between two atoms, regardless of how that attraction happens. Typically speaking, bonds are very, very strong. It requires significant energy to break bonds. Significant energy meaning like we'd have to heat something up to be very, very hot before we dissociated its bonds. So like water, if you boil water, it turns to steam, but it's still H2O. The atoms are still bonded together, even though the atoms have become this really, really scalding hot gas. To turn it into just atomic hydrogen and oxygen, you have to heat the hell out of it way higher, to like thousands of degrees Celsius. So bonds are strong, and it behooves us to understand how they work. All bonds require electrons to be involved somehow. And so this is where the electronic structure part comes in. If we know how electrons are structured around an atom, we can then describe their bonding more effectively. On the screen, I'm highlighting the two types of bonds that we're going to cover in this class. We don't talk about metallic bonding. because it's not covered in enough detail in 161 to warrant it. We've talked about how metals behave, and that's generally speaking good enough. But the other two types of bonding are very important because they're easy to describe and cover a lot of bases. Like, we get a lot out of these two types of bonds, whereas metallic bonding is more advanced and it only really applies to metals and maybe a little bit to semiconductors, which admittedly are interesting, but we can do a whole class on semiconductors and their uses, so we'll cover it there. But anyway, ionic bonds are going to be the result of two atoms transferring electrons from one to the other. When that happens, we will form an ionic bond, and we'll show how that happens in this chapter. Chapter 9 is all about ionic bonds. Or Unit 9, I should say. Covalent bonds involve sharing electrons between the atoms, and I mean literally between, like in the space between two atoms. And as a result, those stick together. We're going to cover that in Unit 10. So our focus today is going to be just, what are ionic bonds? How do I figure out how to make ionic bonds? What sorts of, like, note-keeping and stuff like that is going to help me illustrate or model how bonding behaves. So that's our focus for the day. On the screen, I have drawn a picture of 4 elements, in group 17. I don't know what it is about 2:30. 2:30 is when I want to take a nap, I guess. I'm just yawning all of a sudden. These are all elements in group 17, and what you'll notice is that I have illustrated the electrons as these dots that are on rings. We know that electrons don't live on rings, but what the rings are going to represent is roughly how far away from the nucleus the electrons are. So, over here on the left, this yellow band that I'm filling in is not terribly far from the nucleus, and over here, that's the same band drawn again and again and again. All right. Now, depending on how many bands of electrons or regions of electrons you have occupied, those electrons are going to be further and further and further from the nucleus. And we can fit varying numbers around there. So in the first row in the center, we can only fit 2. The next one is 8. And then you can see that we can squeeze 18 around the other ones. But the periodic table is actually structured in such a way that the element is on the row that corresponds to the number of layers of electrons. So the number of layers is what we call electron shells. We'll get to that in a second. Ionic bonds are metal and non-metal. Yes, that's right. Covalents are non-metal and non-metal. We'll formally define that later and show why that is. So each of these layers is colloquially referred to as an electron shell. And so this is just a term that you will hear mentioned in the both the textbook and the workbook and also on these slides. Now, the other feature that we can consider is how many electrons are on the outside. Because you'll notice that this yellow row, once everything is filled up past it, it doesn't really change much, right? So these electrons in the middle are called core electrons. But on the outside, we have a different scenario. And I can highlight that on all of these, and then we'll just highlight this one too. So The outermost electrons are called valence electrons. Valence electrons are the important electrons that engage in bonding. And they engage in bonding by virtue of being the first things to interact with other matter. If I have two atoms that bump into each other, the electrons that will encounter each other first are the valence electrons. The ones that are closer to the nucleus don't see outside because the other electrons block them. How do they block them, you might ask? They're so tiny. Well, they're all negatively charged and electrons repel, right? So electrons tend to stick to their terrain. If I'm in the third shell, I'm going to stay in the third shell and not suddenly buzz toward the nucleus and be in the first shell. Not for very long, at least. They tend to stay where they're supposed to. And that order is just ordained by how the atoms were formed and when the electrons got there, and so on and so forth. All right. So again, the valence shell is going to be the number of layers, and the period number tells you that information. The number of valence electrons is going to be the group number, but only the ones digit. So since these are all group 17, and the ones digit is 7, each atom in group 17 has 7 valence electrons. You'll notice that my slides say this only works for group A elements, but if we go to Ptable, and I wake it up here, hold on. So I put Ptable on the screen here. You'll notice that, sorry, I'm trying to center it, it's not working. You'll notice that my group numbers are just 1 through 18. We don't really use the old nomenclature scale the group naming scale of 1A, 2A, and then a bunch of B groups, and then 3A, 4A, etc., all the way up to 8A. That's more like the Mendelevian scale. When we saw Mendeleev's periodic table, it had A's and B's on it. Now we just number them 1 through 18. And so the way that we note how many valence electrons there are is we use the ones digit. I meant to circle just the ones digit, and I circled all the digits, because I am dumb and bad. Hold on, let me fix this. There we go. So we're only going to use the ones digit to count valence electrons. So that means that for any given element, I can count how many shells it has by looking at what period it's in. And I can count how many valence electrons it has by identifying what group it's in. So that's what I want you to do. I want you to determine the number of valence electrons and what shell the valence shell is for a given element. So the first one we're going to do is phosphorus. So you're going to have to go to the periodic table and find what row and what column it's in. And I want you to tell me which shell number the valence electrons are in and how many valence electrons there are. So once you got that, type it in the chat. We'll go over the answer in a second. All right, so we'll bring this back on the screen here. So we got to find phosphorus. So here it is. So I have it highlighted. So what row is it in? I don't actually know if the rows show up. Oh, they do. Okay, so this is period 3 and group 15. So with that information in mind, phosphorus should have valence shell 3 and 5 valence electrons. And it totally does. All right. Let's do another one. I want to do O minus. Now, what does it mean to have a minus charge in there? That's going to affect what happens with your periodic table search, won't it? So why don't you tell me the number of valence, first of all, which valence shell are the electrons in for O minus, and then the number of valence electrons. And interpret the charge pretty literally, right? Like, okay, what does a minus do? What do you think it'll do to the number of valence electrons? Because everything below it is all full, right? So, all right, give you a few minutes to consider that. Type your answer in the chat. All right, let's go over the answers here. So we'll go back to the this right here. Let's find oxygen, which is right here. What row is oxygen in? It's in row 2. So it must have 2 shells of electrons. So the valence shell is valence shell 2. It's in group 16, so it should have 6 valence electrons, because that's the ones digit, right? But what does a minus do to our charge? Well, if this was just O by itself, it'd be 6 valence electrons. But this minus is an extra electron, so we just tack that on. So O minus would have 7 valence electrons. All right, and you probably get the idea here. We're going to do one more example, though, because an interesting thing happens when you remove a certain number of electrons. All right, I want you to tell me the valence shell and number of electrons, number of valence electrons, I should say, in calcium with a 2+ charge. Try that. All right. You probably ran into an issue, didn't you? And that issue Comes about from that fact that calcium's over here. It's in valence shell 4, so that's easy enough. And it has 2 valence electrons, so I'm going to write all of that information down. All right. What happens if I get rid of 2 electrons? This happens, right? If I make it plus 2. But is that actually what's happening? If I go back 2 spaces and I remove 2 electrons, that's kind of like this. So if I go back to here, so I'm here on calcium, I'm going to step back 2 spaces. 1, 2. So now it's whatever would have 18 electrons, right? Because I had 20, but then I removed 2. What does argon look like? Well, it doesn't look like it has 4 shells, for sure, right? In fact, the 4th shell I have completely removed. So what I actually need to write is this. If I can get the correct color. Oh, I gotta get the eraser, too. Get rid of this question mark. And that's how many electrons calcium with a 2 plus would have. So we would say that it's actually in shell 3 with 8 valence electrons. And the reason for that is we end up on the same number of electrons as something that has 3 shells and 8 electrons, right? If I'm subtracting electrons and going backwards through the number of electrons I have, I'm digging down into layers that were full, right? So I should just present them as such. We can go back over here and look at this picture here. For, let's say, chlorine. If I were to get rid of 7 electrons, then the next layer down would be the valence layer. Now, what am I doing with all of these layers that have like 18 electrons in them? We're not going to worry about that for now because it's beyond the scope of this class and would require us to talk about electron configurations and stuff like that. We're going to do that in 161. In fact, that's kind of almost all of what we do from like week 4 onward is electron configurations and stuff like that. So, next quarter. But for now, the answer that we want for this is that if I tear away an entire layer, the previous layer becomes the valence shell. And that previous layer will always start with 8 valence electrons, because you end up in group 18 when you do this. And the ones digit is 8. So, keep this in mind, because this is going to become very relevant later on. Alright, so what I want you to do is I want you to look through all these elements and the ions that I also have associated with some of these, and tell me the number of valence shells and the number of valence electrons for each configuration that I have created. Okay? Give this a shot. Go ahead and enter your answers in the chat once you've got them, and we'll go over the results in just a bit. One more minute and we'll go over the answers. All right, so let's bring up the periodic table here. Let's see if I can make it a little smaller. Not so small that it's not useful, but all right. So over here, we're going to say, so valence shell and number of valence electrons. So for arsenic, we'll find arsenic on the table here, which is right here. So it's in row 4, column 15. So it would be valence shell 4. And how many valence electrons would it have? We need the ones digit, so that'd be 5. And we just do this for all of these. So here's boron. Valence shell 2, 3 valence electrons. Then we've got carbon, which is 2 and 4. Then we've got F minus, which is 2, and normally it'd be 7, because fluorine is in column 17. But that minus means add an extra one right there, so this would be 8. Then we got barium down here. Oops, where is my cursor? There it is. Now, when I add electrons to barium, you actually end up over here somewhere, right? In terms of electrons. But we're putting the electrons in the valence layer, so I'm just going to tack on a number of them to whatever I get. So this should be valence shell 6, 2 valence electrons. So we'll write that down for now. But instead of the 2, I'm going to add the 3 extra to it. And so it would have 5 valence electrons. For potassium here, I would have valence shell 4 with 1 valence electron, but I'm going to take away that valence electron. So instead of doing this, it should be shell 3, and then instead of having 0, I should just write that. Oh, excuse me, yawn. There we go. All right, and then finally xenon. We'll click on xenon over here. How many valence electrons, or how many valence shells does it have? It's in row 5, so that's 5 valence shells. And then how many valence electrons? It's in group 18, so it should have 8 valence electrons. All right. So that's very straightforward. We can write out all this information. What we are going to concern ourselves with here is this. Because in the next section, what we're going to do is we're going to learn a strategy to draw pictures that convey this information. Now, again, we only care about the valence layer, because those are the electrons that are going to bonk into... Oh, I can Oh, geez, I had myself muted. I'm sorry. Okay. I'm sitting there talking, and, like, no, I'm assuming that you guys can hear me, but you can't, because I didn't have it, the mic open. Okay, so it is working now. You should be able to hear me now. Yeah, my program crashed, so whatever I used to open this window, so where's my periodic table here? Whatever, it doesn't matter. No. I sometimes when I click on that, it doesn't work, and then everything breaks, and then the stream just cuts out. And it's like, oh, that's awful. I have to fix it. So it should be reconnected. It looks like it is because you can hear me now. So yeah, what was I saying? What I was saying was the number of electrons in the valence shell is going to be what's important to us. And we're going to consider that by drawing a structure. And so that's going to be our objective here, is that we're going to be drawing pictures of things. So this is where C.N. Lewis comes in. Not C.N. Lewis, G.N. Lewis. C.N. Lewis might be somebody else. I don't know. So G.N. Lewis, of which you can see in his journal down here, had this schematic for drawing electrons as like a cube, like the vertices of a cube. And his idea was, oh, okay, C.S. Lewis, that might be who I was thinking of. Yeah, the author, that's right. And you can see that on the corners of this cube, what he was doing was drawing valence electrons. And he said, okay, lithium has 1 valence electron, so I'm going to put it in one corner of the cube, whereas chlorine has 7. I'm going to fill in all 7 of the corners of the cube. And then you'll notice down here that he has sodium gets 1 and chlorine gets 7, and he's trying to fill the cube. And so his idea was, okay, maybe 8 is a special number. And we're going to try and get to 8, which it turns out it is, because he had an understanding of bonding, which we're going to talk about later. And so what we now do is we have simplified his notes to what is called the Lewis symbol. And the Lewis symbol is a very simple process. This is probably the simplest thing that you're going to do in this class, but it's also very important. So the first step that you're going to do is for any given element, you're going to write its symbol. You're going to then put dots around the 4 sides of the symbol, 1 per valence electron. And if it's an ion, put brackets around it and add the charge. So let's do an example of this, and you'll see how easy this is. So we're going to do sodium first. How many valence electrons does sodium have? If you look at the periodic table, it's in group 1, so it's only got 1 valence electron, right? So step 1, draw the atomic symbol. There you go. Step 2, draw a dot for each valence electron. I'm going to put a dot over here. It's not an ion, so you skip step 3, and it's done. Hooray! Easiest thing ever, right? You're going to put a dot down for each valence electron, and if there's only 1, you just draw 1. If there's 8, you draw 8. If there's 0, you don't draw any at all. You don't have to go back to the previous layer. We're going to just imply that there's 0. All right, so let's do oxygen. So again, draw the atomic symbol. I'm going to give you a few seconds to draw the atomic symbol for oxygen. All right, hopefully you drew this. Now we're going to put dots down. And we get a kind of an oddity here. When we put down dots, what the generic rule is that, well, if electrons repel, you're not going to stick them all together on the same side, right? So I'm not going to do this. That's ridiculous, right? Those electrons would spread out as far as they could. So there are 4 sides available, so I'm going to put an electron on each of the 4 sides. And then and only then will I start pairing them, because I have to. Now they are essentially as spread out as possible. Why do we only have 4 sides? We'll get to that in 161 when we talk about geometry. For our purposes, we're just going to assume that each of the 90-degree sides here, north, south, east, and west, can hold up to 2 electrons. It's not an ion. So we skip step 3, and there you go. It's done. Now, if it were an ion, so suppose it was O minus, then what we would do is we'd add the extra electron, and then I would do that. I circled my charges just to indicate that that's what they are. You do not have to do that, as long as you are clear. All right, so now that you know how many valence electrons all these have, because you literally just did all these examples, right? I want you to draw the Lewis symbol for each of them. So go back to the exercises that you just did. Find your arsenic, find how many valence electrons it has, draw the correct Lewis symbol. Remember, 1 electron per side until you fill up all 4 sides. I'll give you a few minutes to do that. We'll go over the answers and then take a break. You want to say hi? Say hi. Say hello. What? Say hi. One more minute, we'll go over the answers. All right, let's go over the answers, and I'll just bonk my microphone while I'm at it here. All right, so since we've written down all the valence electrons, I'm going to write those over here. So valence electrons. So we're going to go 5, 3, 4, 8. This should be 5. We're going to call that 0. All right, so I'm going to just draw all my Lewis structures. So arsenic would look like this. Now, if you put the double on any other side, guess what? It's okay. There's no orientation here that matters, because I can just rotate the atom around however I want to in space, yeah? As long as there's only one pair of 2 here, you'll get the correct answer. So for boron, there's 3, so I put them on any 3 sides that I want. Doesn't matter. Now for carbon, there is only one way to do this, and it's to put 1 on each side. Oh, excuse me. All right, now let's do fluorine with a minus charge. So fluorine would normally have 7, but the minus makes it have 8. And because this is an ion, we're going to put a charge and some brackets around it. There's my barium with a 3 minus charge. I've added 3 extra electrons. Now for potassium, here's what it would normally look like. If I'm going to make it K+, I don't actually just draw in all the dots. The convention is, if you land on 0, even though we know that the previous layer down is the valence layer that has 8 in it, we just draw it as empty. And there will be a reason that makes sense coming up later today. And then finally, xenon. There you go. You'll notice I'm drawing some of these kind of like circles or whatever. It's hard to draw an electron big enough on the projector here. So, because if I just do this, you can't see them, right? So I'm trying to draw them big enough so they look kind of dumb. I apologize for that. All right, Maya says it's time to take a break because I had to pat her. So I'm going to put this on the screen. And, oops, I got to clear that. We will get the music going again. If I can find the right song. Yeah, there it is. Okay.
Every day with rain あなたと Every day with rain 二人で Every day with rain 固めて I'm gonna wake up with a smile I feel laugh it like a child Believe あなただけ We are all real That is my loving 雨の中で踊る Come like a journey to find a happiness そう愛の香り Come to me Hear the wind blows 世界を Hear the wind blows 二人で Hear the wind blows 固める I'm gonna wake up with a smile I feel laugh it like a child Believe 二人だけ
All right, we're back. All right, what were we doing? That's my favorite song on the whole track, or the soundtrack. So I was just sitting there like bouncing in my chair, and then like, oh shit, I have to actually do something. I have to do my job. Let's see here. So on the previous slide, we drew pictures for all of the atoms and ions that I gave you, and there's a cat now here that is demanding my attention. We noticed that at the very last one that we drew xenon. We also drew fluorine with a minus charge, and both of those had 8. Now, a particular thing about 8 is that where would you put a 9th one anyway, right? I've already got 2 on each side. I guess I could put a 3rd one. But instead of doing that, our periodic table actually goes to the next row. So you never will see 9. 8 is the highest it will go. Furthermore, elements that have 8, such as xenon right here, I don't know why that happened. There we go. Such as xenon right there, tend to be particularly stable. In fact, all noble gases are like this, and the thing that noble gases have in common is that there are 8 valence electrons around their around their valence shell. And so this is a special situation that we actually have given a name to. This is called the octet rule. If an atom has 8 valence electrons, it tends to be stable. I'll highlight more because more is important too there. So this is called the octet rule. So what atoms will try and do is they try and gain or lose electrons until they have 8 valence electrons. Once they've satisfied the octet rule, they are in their more stable form. So this is why certain ions will form. So in the previous example, when we had F minus is an expected ion that will form from fluorine, because giving it an extra electron will cause it to achieve 8 valence electrons. It will be more stable than it would have been if... Sorry, I'm trying to lecture, and I have this cat in my ear just going... I don't know if you can hear her. You might be able to hear her. Maya, you gotta stop. I can't... She keeps just making purring noises next to me. Alright, let's look at some examples here. How do we get to 8 valence electrons? Oxygen only has 6, so what we're going to have to do is we're going to have to either add or remove electrons. Those are the only options, right? So we need to get to 8, and so the simplest way to do this would just be to add 2. And so there's those 2. Let Maya lecture. Maya, they want you to lecture. Do you want to give a lecture? Maya? Maya? Now she doesn't want to say anything because I took the headset off. Maya says homework is to pet her 5,000 times. She's like, she does this rubbing thing. She's rubbing against everything because she wants me to very obviously pet her. And that thing that she's chosen today is the arm of my chair. So, like, I'm just very slowly oscillating back and forth because she keeps pushing the chair. And it's breaking my concentration. So, Maya, you gotta go. We gotta scoop you up and put you down on the floor here. There you go. She jumped right back up. Oh, great. Okay. So, here's our example for oxygen here. So, I'm gonna add these 2 electrons. Those ended up here. And so now my total number of valence electrons is 8. So this ion would be more stable than just oxygen by itself. Now all of our atoms are going to tend towards getting an octet, which means that we're going to have to either add electrons or remove them. Atoms that have more electrons will tend to add them because it's closer, it's easier to do that. Atoms with fewer electrons will tend to get rid of them. And by fewer and more, I mean valence electrons specifically. All right, here's our calcium atom. Calcium wants to fulfill the octet rule, so what do? I could add 6 electrons, or I could give away 2 electrons to completely remove valence shell 4, which means that the next shell down would be the valence shell, which still counts. We're going to pick the easier option. So whenever you're faced with a choice, should I add this many or remove this many? Pick the option that requires fewer electrons, because nature's lazy, right? Which will require less effort? Getting rid of these 2 electrons. And so that's what we're going to do. So our mission is to figure out what ion, everything forms. And the way that we're going to do that is going to be governed by the octet rule. So when I give you an element, you're going to follow the octet rule and then predict what ion is formed, if any. All right, so to summarize here, elements will either give up electrons or they will take electrons with the goal in mind of achieving an octet. Now, metals that are in groups 1 through 3, I'm going to rewrite these without the A designation here. Actually, I got to do it this way. 1, 2, 13. Tend to have few valence electrons. They have like 1 or 2 or 3 valence electrons, so they pitch them. Elements in groups 15 through 17 have 5 to 7 valence electrons and tend to accept them because they want to get to their octet. Elements that are in group 18 have 8 valence electrons and don't need any more electrons, so they don't react. So noble gases are already stable. They don't do any chemistry. Group 14 is the weird one because it's equidistant. It could either gain 4 or lose 4. So what does group 4 do? Specifically carbon does whatever the hell it wants to. And when it does that, you get a very interesting branch of chemistry known as organic chemistry. So we're actually going to talk about carbon in so much detail that we have to spend a whole year talking about it. Because it is in the Goldilocks just right area to do all sorts of really cool things. And we're going to see none of them in this class, unfortunately. So we're not going to have you predict an ion for any element in group 4 because it's difficult to do. Excuse me. It depends on circumstances and other reactants and what you're working with, which direction it will go. So, all right. So on the screen here, for these 6 ions here, I want you to answer this question and this question for both of them. So figure out which ion you're supposed to have for each of these elements by following the octet rule. And then what I want you to do is I want you to tell me how many protons and electrons does each of the ions have once you've made it. Okay, so select the correct ion for each thing. We're going to put the charge on it, and then we're going to count the number of protons in this column right here, and the number of electrons in this one. Then finally at the bottom there, I have a bunch of ions. Some of them should form, but others should not, because they don't satisfy the octet rule. Draw a circle around the ions that are expected to be stable, and then draw an X through the ones that are not. So just copy down all the ions, and then circle or X them. All right, I'm going to give you 5 minutes to do all these. We'll go over the answers in just a bit. 1 or 2 more minutes, we'll go over the answers. All right, let's go over the answers here. There's my pen. It's not where I was looking for it. Okay, so for each of these, what we're going to do is draw how many valence electrons it should have around it. Oops, I didn't mean to do that. So chlorine is in group 17, so it should start with 7 valence electrons. So if I go boop, 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 boop. So that's what it starts as. In order to get to an octet, I got to add an extra electron, which means that it's now this, right? And then how many protons and electrons does it have? Well, 17 and then 1 more than that for electrons. I'm going to run out of space if I do this way. So let me go over to here. We'll just put all of those on the screen here. All right, so for barium here, here's what barium looks like. To get its octet, I'm going to get rid of those 2. So it looks like that. And then how many protons does barium have? Well, according to the periodic table, I don't know because I threw it in a pile and then put it over on a bookshelf. So let me reach over and grab it. There we go. I have a laminated periodic table. You probably hear it. Let's see. Barium is 56 protons. So protons. And then electrons would be 2 less than that, so 54. All right, here's my nitrogen. Nitrogen is in group 15, so it has 5 valence electrons to start. To make it have an octet, I'm going to have to give it 1, 2, 3 extra electrons, right? So there's its charge. How many protons does nitrogen have? Well, it's element 7, so there must be 7. And then with a 3 minus, it would have 10 total electrons. Remember that with total electrons, that is very different than valence electrons. So just be careful of that. That is a point of confusion. Valence electrons and total electrons are not the same thing. All right, sulfur is in group 6, so it gets, or 16, sorry. So it gets 6 valence electrons. I'm going to add 2 valence electrons to it to give it its octet. And then let's start counting stuff. So sulfur has 16 protons, and total electrons would be 18 at that point. And then we got phosphorus, which looks like this. I drew too many. Oh, no, I didn't. Okay. So that's what phosphorus looks like. I'm going to add enough electrons to give it an octet. That was 3. Now I'm just hiccuping like crazy because my body is broken, I guess. I don't know. Now I can count protons, so 15 protons, and then plus the 3 electrons would give me 18. You're noticing you're probably noticing that I am landing on 18 a lot. Yeah, there's a reason for that. And then finally, rubidium here. Rubidium with its 1 valence electron. We're just going to get rid of that. Has 37 protons, but only 36 electrons. All right. Now, if we look through all these numbers that we landed on, you'll notice that all of the numbers for electrons, for the total when we're done, are all numbers of electrons that noble gases have. And yeah, elements that are in groups 1 or 2, when you remove electrons from them, they're always going to end up over like that, because they'll back up into the previous noble gas. Since noble gases are expected to be stable, elements that remove electrons and land on a noble gas electron configuration should also be stable, and turns out they are, because they follow the octet rule. Alright, now we have to go down here to this part and circle the ones that are stable and draw X's through the ones that aren't. So aluminum has 3 valence electrons. If I remove them, that should be stable. So this is good. We can show that here. So aluminum, 1, 2, 3. Oh, I'm going to get rid of its 3 electrons. Yay, we did it. How about selenium? Selenium starts with 6, and I have to add 2 to it by doing that. That checks out to me, too. What about bromine with 7 valence electrons before we do anything to it? Now I'm going to get rid of 1? What? That doesn't make any sense. No. And this is the sort of process that I want you to go through as you do these. So I'm just going to give you the answers to them. Bromine doesn't work because we removed an electron instead of adding one. So that's no good. P5 plus doesn't work because even though you end up on an octet, it's not the fastest and shortest way to get there. So P5 plus should not be stable. It takes the long route. And then CS minus is also unstable because if we add an electron to it, it actually wanted to get rid of its electron. So be careful of those. Alright. If you are paying attention to the elements I've been picking, you've probably noticed that I did not pick anything for groups 4 through 12. There is a reason for that, and it's because the octet rule doesn't work for those elements. So if I gave you iron, for instance, you could draw dots around it, but iron and other transition metals, and also lanthanides and actinides, do not follow the octet rule. They follow a different rule. And that rule is related to 18 electrons instead, which is why that when we went all the way back here, if I go back to this picture, you probably noticed that how many dots are in the third ring and the fourth ring here. They all had 18. Yeah, be careful with the pluses and the minuses, because the instinct to do everything backwards is very strong. I'm trying to zoom out here. There we go. So, because the octet rule doesn't apply to something that has 18 valence electrons, we had to use different rules for that. We're just not going to do Lewis symbols for elements that are transition metals. So we won't draw Lewis symbols for these elements being these ones right here. So some elements just will not have a Lewis structure, and by virtue of, even if they got to an octet, they might be more reactive than in a different form or whatever. And we're going to discuss that in much more detail in Chem 161. Now, even though you can't form Lewis structures for them, you can always form an ion. And so we're going to form ions for you, and it'll be your job to solve for the composition of the ion due to the electronic structure of what's going on around it. So, for instance, if you have two chlorines attached to something, and chlorine is very electronegative, it pulls electrons towards itself. We're going to talk about what that means later on. The magnesium must be giving up those electrons. And you would predict, oh, okay, well, if each chlorine took one, magnesium must give away two or something. We're going to explain how this is done in the next section here, but you can sort of predict it and calculate it is the goal here. And so all those charges down there, iron plus 2, tungsten plus 6, cerium plus 3, those are all going to be able to, you'll be able to calculate those charges without having to rely on the octet rule, is what I'm saying. So for the most part, don't worry about how to figure out what charges are present for transition metals, because it follows a weird sort of set of rules that we'll spend time on in 161. All right, the last thing that we're going to do today is we're going to show how we manipulate electrons to give octets to form ionic compounds. So when we form an ionic bond, we need to form ions first. And the reason for that is because if I have two charges that are oppositely charged, they will attract to each other. And the attraction that they form or establish is called an ionic bond. Now, not all atoms are ionic. They may be in the elemental form for whatever reason. For example, I can have sodium as an elemental atom. It can be sodium metal. Just like you can have aluminum metal. You could also have aluminum with a +3 charge, which would be an ion. Just like I can have sodium with a +1 charge, which would be an ion. But what happens if I put two things together that are neutral electrically, but have the potential to pass each other electrons? I'm going to come back to this lattice here real quick. I just want to get to what I'm talking about. And so that's what's going on here. All right, where is this going to pop this up here? It's going to pop it up right on the wrong window. So I need to move this over to this one. All right. So what we're going to do is we're going to watch what happens when I take elemental stuff. And so when I say elemental, what I actually mean is this. So I'm going to take sodium metal where it's not an ion. And I'm going to take chlorine gas where it's not an ion either. These are the elements that I have. I'm going to mix those together and see what happens. And the end result is that we get this guy doing chemistry for us. All right, this is Lonnie. Lonnie is an instructor at UC Berkeley. I've never met him. I just use his videos for like these one or two things. Oop. Comcast dropped some of my frames, so. This is Lonnie. He's going to do an experiment in his lab. I have this muted because I'm going to talk over him, but that's okay. So what Lonnie's going to do here is he's going to create sodium chloride. You don't need the subtitles, so I'm going to turn this off here just because it's distracting. So the first thing he's going to do, I'm going to hit pause here, is he has this canister with this hose that is in a container right here. And if you look carefully, you can see that behind this container, you can see his lab coat, and it looks a little yellow when you are looking through this container. That's the chlorine gas. Chlorine gas is this pale yellow, super toxic substance. And the way that Lonnie is protecting himself, because this is super caustic, like if he breathed any of it in, it would be very bad for his lungs. But what we have here is a fume hood. This little space on the ground, it's not the ground, it's on a table here. Putting anything on this will just suck fumes into it. And so he's perfectly safe. Any chlorine that does escape will get sucked into the fume hood. Next thing he's going to do is chop off a piece of sodium. We store sodium under mineral oil. He's going to rinse that oil off by putting it in hexane. No water can be used in this experiment because the water would react with sodium and explode. We saw that on the first day of class, so we can't have that happen. Once he's satisfied with the rinsing of the sodium, he's going to put it in this ladle and then heat it up. The heat is just to make it melt a little bit to increase the surface area, and also give it enough energy so the reaction will start. It's kind of, think of it like striking a match, except the match is a ball, not a bowl, but a ball of sodium. And once it's lit enough, he's going to put it into the container, and it should react immediately. And it turns out, because I've seen this video 75 million times, it does. So now all he has to do is move this up and down so that he reacts with all the chlorine. And so this chemical reaction is taking place to form sodium chloride table salt. Now, it's actually salt in the gas state. Believe it or not, you can make an ionic compound in the gaseous phase. You can have table salt as a gas. It means that everything has to be extremely hot, which, as you can see, when he takes out the ladle is red hot. So this reaction was definitely at an incredibly high temperature. Now, unfortunately, he doesn't give enough time for this to coalesce, but if you did allow it to do so, we'll put the caption on the screen here. So, he has table salt from a previously done experiment, but eventually what would happen is that this salt that's down here behind the status bar is edible. It's the same salt that you and I would put on food. And so he's going to take an egg, which you should never do in the lab, because you're not supposed to eat in the lab. It's dirty and there are chemicals present, and like you're like 2 feet away from a chlorine gas cylinder. What if it blew up on your feet, dude? But yeah, he could totally eat the salt that he prepared, hold up his egg in victory, and another day, just another day on the job for Lonnie at his lab. Alright, so what did exactly we do? Because I wanted to make an ionic compound, I need to form this and this, right? So in order for these to attract, I have to have something positive and negative. Here I don't yet. And here's what happens. When sodium that is energized approaches chlorine, it basically gives the electron immediately over. There's enough energy in the sodium because it was hot or heated or whatever that it bunked into the chlorine. Excuse me. It bunked into chlorine and then just immediately gave up its electron because both of them needed it, right? Or that both of them needed that course of action. Sodium wants to get rid of its electron so that it has an octet. Chlorine wants to accept an electron because then it will have an octet as well. And once this has happened, this sodium becomes this, and this chlorine becomes that, because this is added, or I'm sorry, sodium has removed an electron, so I put a plus there. Chlorine has added an electron, so I put a minus there. And then now that they are oppositely charged, now they will form the ionic bond. So that's the gist of how ionic bonds are formed. Step 1 is going to be draw the Lewis structures of the elements involved, and then step 2 is shuffle electrons such that everything ends up with an octet. So there's our visual example there. Everything has an octet. So the formula that we get is NaCl, because those are the ions that were necessary to go into this. And there's our summary. In order to make an ionic bond, you have to have charges, so you have to have ions, and you make your ions by following the octet rule. But what we have done in this section is, instead of just creating electrons from nowhere or deleting electrons into the ether or whatever, we are removing electrons from atoms and giving them to other nonmetals. And so that's where our distinction comes in for what elements are necessary for an ionic bond. You have to have a metal because you have to have something that gives up electrons. And you also have to have a nonmetal which accepts the electrons. If you have two metals or two nonmetals and you try and do ionic bonding, what you end up finding is that that doesn't work. Two metals would want to ditch electrons on each other, but they can't because they end up with the other person's electrons. And for nonmetals, two nonmetals bonding, you have too many electrons. Nobody can reach an octet by giving stuff away. They can only reach it by taking. Alright, so let's try and put some ions together based on the octet rule. So for instance, I'm going to skip ahead to, instead of saying I have potassium with one valence electron, what ion does it form? We're going to skip ahead to what the ions are and figure out how to make an ionic compound out of them. So the first two ions that I'm going to put together are these two. Potassium with a +1 and sulfur with a 2-. Now, if I was to put these together as is, the charges would sum together. +1 and -2 would give me a formula that looks like this, right? Because 1 plus -2 is -1. Well, that's not an ionic compound. That's an ion on its own, because the total charge of any ionic compound has to equal 0. Or in other words, the total positive will equal the total negative. So I clearly didn't have that. I have too many negative as opposed to positive. So this is not an ionic compound. This is just a compound. What I need to do is add in an extra potassium so that everything balances out and there is no charge at the end. And that's our formula. So when I mix two potassium ions together with one sulfide, I can get potassium sulfide because all the charges balance out and cancel to 0. So that's your quest. 1, make the Lewis structure. 2, find the correct ion that should form for that ion. Or element, I'm sorry. And then 3, transfer electrons from one atom to another in order to satisfy the octet rule and figure out what the charge of the substance, or I'm sorry, the formula of the substance is. All right. I thought I hit erase everything. I think I hit eraser. Yeah, there we go. That's also not it. My goodness, why isn't this working? There we go. All right. Now, if you have a transition metal, I can't tell you this first step where I say, oh, how many valence electrons does it have? I don't know, right? But something happened, and the result may have been this, right? So if I have iron with a +3 charge and along comes chlorine, and chlorine says, oh, guess how many electrons I have? I have 7. I need 1 extra electron. Well, iron is going to say, okay, I have to erase this. iron can still just give away electrons to fill in whatever gaps are needed. And we have already assumed this. Because when we get down to here, and we want to write the formula for what we did, now we have to solve for iron. Well, I know that if I have Fe3 plus and Cl minus, I need 3 of these to do that, right? So if I took iron and mixed it with chlorine, the end result that I would get would be FeCl3 if the ion I formed was plus 3. But now let's assume that we're going to go in the opposite direction. So I've started with this, and I want to figure out what iron was used. Here's what we do. We're going to split this into the ions that we know exist. For example, we know what Cl is because Cl follows the octet rule, right? It would do this. Well, what must this part be over here? Must be that, right? Because what other charge would balance out the total negatives there? So that's how we're going to solve for these things, is we're going to do this sort of approach. All right. So I'm going to give you this ionic compound, Fe3 plus and O2 minus. What would the ionic compound be that forms between those two ions? I want you to try and balance the charges. And then, if you think you have the right answer, break them into their ions and see if you get the original charges that you predicted. Okay? I'll give you 2 minutes to write down the formula, put it in the chat. We'll go over the answer in just a second. I had to step away from the computer and go eat something because I'm absolutely starving. I'm still chewing, but I don't want to chew in the microphone. But you have the right answer, so I'm going to put these problems on the screen here, and I want you to do the same thing. Now you just have to put all the steps together. So predict the ionic compound by first predicting the ions. I'll check back with you in just a bit. I realized, looking at the clock in the kitchen as I was hungrily devouring some garlic bread because I'm really looking forward to more Swedish meatballs for dinner here, that my microwave timer said that we only had 1 minute of class left, so I'm going to just quickly write down the answers here. And we'll go over how we get these at the start of tomorrow's lecture. Maya says hi, by the way. Maya. All right, so there's the answers for those problems. We are out of time for today, but we'll go over how to do these as a warm-up for tomorrow. So I do want to thank everybody for coming out to the lecture. Make sure that you get quiz number 5 in by tomorrow. That's when it's due. There is a 24-hour period after that you can still turn stuff in if you need to. Yeah, that's all I got. So we'll finish unit... Oh, it's... Hold on, stop the music. Hold on. I just realized that I have the wrong scene collection set here. Hold on. All my notes at the bottom. Let me just do this. Okay. That was really weird. I don't know how this... What did I do? I thought I clicked here. Okay, that's better. I don't know what happened there. I must have clicked something stupid. Oh, I know what happened. It's been like that when my OBS crashed, so I was on the wrong scene collection because it went back to what I had before when I opened it. Okay, so there we go. Everything at the bottom should be correct now. Yeah, so I apologize that it's probably said Chem 121 down here at the bottom for like a third of the lecture. When my program crashed, it reverted that, so it's back to normal. But yeah, that's the correct assignment. So the quiz for Unit 4, the quiz number 4 for Unit 7, and I'm all mixed up now because everything broke. Right? So quiz number 4, which was Unit 7 and 8, is due tomorrow. Make sure that you have that finished by then. Closes on Wednesday. We'll start the music again. We'll finish Unit 9 tomorrow, and that's pretty much all I got. Have a good night, and take care.